I'm Norman Wildberger, and welcome to our second lecture in this course on linear algebra. Before we start, it might be good to say a few words about how you might think about working in this course. For every 1 hour lecture in this series, probably you should be working for 3 or 4 hours on your own, reviewing the material, doing extra examples in the spirit of the ones that I show you, and also working on the few exercises that I hand out. So last time we introduced basic ideas of linear algebra in the sense of affine geometry in the plane. We talked a little bit about vectors. Today we're going to talk about geometry with vectors. Now, last time we worked in the framework of an affine grid plane. I remind you, that was something that we got by finding, first of all, a family of equally spaced lines in one direction, all parallel, and then another family of equally spaced lines in another direction, all parallel, and using some basis vectors in those two directions to describe relative positions between points. So, for example, in this situation here, let's suppose that we choose this vector as the basis vector of the lines in this direction. So this vector from here to here is the same as the vector from here to here, well, the same as the vector from here to here, and that's called E1. And let's, in the other parallel lines, let's choose this as a basis vector, E2. So this is also E2, this is also E2, this would also be E2, and so on. Then I remind you that if we want to express a vector V, like this, in terms of these two basis vectors, we can say to go from here to here means we have to go in the E1 direction 3 steps, and then in the E2 direction minus 2 steps. So the vector V is written 3 minus 2 with reference to this fixed grid plane. And in terms of the addition of vectors and multiplication of vectors by numbers that I talked about, this could also be written as 3 times the basis vector E1 plus minus 2 times the vector E2. So this ties the geometry to the algebra, and that's good. But a natural question is, do we need all the time to go through the work of drawing a grid plane to start off with? Well, it turns out that we can avoid that, and today we're going to do geometry without a grid plane like this for reference. To make that work, we're going to establish first some basic constructions that you can do, starting with basically a white page, and just the notion of vector and parallel line. So our first basic construction is how to translate a vector. Here's a vector V from this point to this point. And suppose we want to translate that vector so that it's starting from, say, this point. Well, we're only allowed to use parallel lines, so here's how we do it. First, we establish a line through the 2 starting points. Then we draw a line parallel to this one through that vector. And then another line parallel to this one through that vector. So we need to go a little bit further here. And then this vector here, from this point to this point, that's going to be another copy of V. It's the same vector, but now instead of starting from here, it's starting from here. So we've translated it as required. Our second construction is how to create equally spaced points. So we're starting off with a line and 2 points on it, and we want to create some more points that are equally spaced to these ones. So what we'll do is we'll start with another line parallel to our given line, and then we'll choose any other line through the 2 points parallel to each other, like that. And that forms for us a little parallelogram. And then we can join things up like this, and parallel to it another line like this. And then we found our third point equally spaced to that first pair of points. And you can see we can keep going with this crisscross pattern, using all these lines parallel to these ones that I've drawn to continue creating a sequence of equally spaced points. Now our third construction, very important one, is how to add two vectors. We've seen this before, so here's a vector v and here's a vector u, but let's just make sure that we know how to do that. So how do we add those two vectors? Well, instead of using those two vectors, let me draw a separate diagram. So I'm going to draw another vector here. And so I'm translating this vector there using that first technique. And then I'm going to translate this vector so that it's emanating from here. Let's say that ends up being something like this. So there's u. There's v and u. And now we can create a parallelogram. Parallel here. Parallel here. So this vector here is also u, and this vector here is also v. So we've created simply a parallelogram with sides v and u. And now the diagonal of this parallelogram is u plus v when we've gone this way, and when we've gone this way you can see that it's v plus u. So v plus u and u plus v are the same, and in fact we didn't have to go through the whole parallelogram. We could just go through this side and that would be enough, or we could go this vector followed by this vector. Either way we'd get the sum of the two vectors u plus v. Our next construction is to show how to bisect a segment. So here we have 2 points, and we want to find another point which is halfway between them. Well, what we do is we're going to use, again, a parallelogram. So we have to make a parallelogram, and let's arbitrarily choose some line through our first point, and another line through the other point, parallel. And then we can choose any other line through the first point. Let's say that one there. And parallel to it, a line through the second point. So we've created a parallelogram so that the original vector is a diagonal. And then what we do is we draw the other diagonal. The other diagonal of that parallelogram gives us then a point which is then going to be a midpoint of this segment. So this vector and this vector are going to be the same. How would we trisect a segment? Divide into 3 equal vectors. Well, we've talked about this before. So one way of doing that is to create another line through one of the points, and then create on it a sequence of 3 equally spaced points. So choose any point, and then create another point that's equally spaced, and then a third point equally spaced. And then we draw parallels to our endpoint, and parallel to that, another line there, and another line there. And that gives us then our 2 points that we're after to divide our original segment into 3 equal pieces. And our last, but not least construction, is how to subtract vectors. So here's a vector u, and here's a vector v. And we want to understand the difference between v and u. This is a very important construction, so make sure that you understand this completely correctly. So what we're going to do now is we're going to put those vectors together, and I could use one of the vectors and just translate one onto the other one, but I'm going to make a separate diagram emphasizing the fact that it doesn't have to be in the vicinity of these 2 vectors. It could be anywhere. All right, so let's create a diagram by copying first our vector v, say there. That's our vector v. That's using our notion of translating a vector. And now we're going to take a copy of u and translate it so that it's starting here. So it's in that direction. So let's say that's the vector u. All right, so we've put the two vectors together so that their tails are touching. And now what we're going to do, we're not going to add these two vectors. That would mean creating a parallelogram. We're not going to do that. We've already got enough information. It's now the line joining those 2 points which is going to be the difference. And which direction it's going to be is up to us. It depends which difference we want to take. So suppose for the sake of argument that we're going to use this vector here. So what is this vector here? Well, it has the property that if you take v and follow it by this vector, so v plus this mystery vector is going to be the same as u. Well, that means that this vector is u minus v. And a good way of remembering that is the vector that comes first is at the head, and the vector that comes second, the subtracted vector, is at the tail. So it's final minus initial, or endpoint minus starting point. That's the vector u minus v, the difference between those two vectors. And if we wanted v minus u, well, it would be exactly the same, except that the vector would be pointing from here to here. So this would be the vector v minus u. So this is a very important construction. We'll put a little star beside it. Make sure that you know how to form the difference between two vectors and know what the difference means in terms of this particular little triangle. All right, now let's establish some basic laws of vector arithmetic. So we've defined these various operations. Now let's show some rules that these operations satisfy. So the first one we've already talked about, but it's worth pointing out again, that vector addition is commutative. So here is the vector u, here's the vector v. We form this parallelogram, and u plus v is that combination. First u and then v, so there's u plus v in red. And on this side there's v plus u, which is equal. So u plus v and v plus u are the same. Here is the associative law for vector addition. We have three vectors, a vector u, a vector v, and a vector w. And I've shown you the vector u plus v. There's u plus v. And I've shown you also the vector v plus w. So it's starting here, there's v, there's w. So from here to here, that's v plus w. So on the left-hand side, we have u plus v plus w. What does it mean? It means we need to take the vector u plus v, this red one, and add w. So there's u plus v, and there's w. The combined sum is that vector there in black. On the other hand, u plus v plus w is first u and then v plus w, which we've established is this green one. So again, we're going u plus this vector, and again the combination that results is u plus v plus w, this black one here. Okay, so these two are the same, and because they're the same, we can just write u plus v plus w, and we don't have to worry about where the brackets go. Okay, over here we've got a diagram illustrating this distributive law. Alpha and beta are numbers, rational numbers. V is a vector, and we're saying that alpha plus beta v equals alpha v plus beta v. And I've illustrated that in this case here, so maybe it's a little bit unambiguous, but let me clarify. So the vector v is the red one from here to here. Okay. And I'm interested in some other multiples of that vector v. So there's the vector that's 3/5 of v. And this vector here is 4/5 of v. And how do I know that? Well, because I've taken some other line and I've chosen equally spaced points on it. And I've gone from here to here. That's where the V starts. That's 1, 2, 3, 4, 5. So I've divided this segment into 5 pieces and drawn a parallel. So now if I draw a parallel through here, then that's 3 steps out of 5. It means that this vector is 3/5 of V. Okay. What is this big vector here? Well, that's when we go all the way from here to here. So there's altogether 7 steps. So it's 7/5 of V. So this big vector is 7/5 of V. And what is this vector from here to here? Well, that corresponds to 4 steps. That's 4/5 of V. So it shows us that 3/5 of V plus 4/5 of V is equal to 7/5 of V. So exactly this kind of distributive law. And the last diagram illustrates that the negative operation acts a lot like adding the negative of a vector. What's the negative of a vector? Well, that's an important thing to realize. The negative of a vector is the same vector in the opposite direction. So here's the vector V from here to here. And over here you have this something that's parallel to it, but from here to here is in the opposite direction. So this is the vector minus V. So what does this diagram show us? Well, there's V, there's U. So if we look at this black one going from V to U, then that's a case of subtraction because that's a vector from the head of one vector to the head of another vector. And what it is then is the U vector minus the V vector. Final minus initial. That's what this vector is. That's U minus V. Now how would we describe this vector, which is parallel to it and so equal to it? Well, we can also, from this diagram, see that it's U plus this vector. And this vector we've said is minus V. So when we go this way, we get U plus minus V. When we go in this part of it, we see that it's U minus V. And that shows us that the vector U minus V is the same as the vector U plus minus V. So that's another basic rule that we use quite a lot. Now let's talk about a very important idea of affine combinations. That concerns a situation like this, where we have a line that we're interested in. We have 2 points on that line, A and B, and we think of those points as sort of reference points on the line. And we would like to describe other points on the line in terms of the 2 given reference points. And what we do is we imagine that we are an observer somewhere off the line at a point O. Now where this point O is irrelevant. It's just some fixed point that's off our line. And we're looking at this line from this observer's point. So we have some vectors. The vector joining O to A, we'll call that little a. And the vector joining O to B, we'll call that little b. And to start off with, we're going to be interested in the midpoint of A and B, the point that's halfway between them. And we'll call that point C, and we'll say that the vector joining O to that point is little c. Okay, so what we'd like to do is we would like to express the vector C in terms of the vectors A and B. The important thing in a picture like this is to get a hold of the other side of the triangle. And that's a case where subtraction of vectors is relevant. So if we say consider the vector from A to B, that's going from the head of A to the head of B. So that vector is the vector B minus A. And I've drawn it over here. There's another copy of it so you can see it very clearly. That's the vector B minus A. And now we can ask, well, how do we get from O to C? We can get there with 2 steps. First we can go from here to here, and then we can go from here to here. And both of those steps we know, because the first vector is A. That's clear. Now what is this vector from here to here? Well, it's in the same direction as B minus A, but by assumption, it's exactly half as far. It's half of the vector b minus a. So we write a plus 1/2 of b minus a. And now we use the rules or the laws for vector arithmetic that we talked about in the last slide. We can write the 1/2 of b minus a as 1/2 of b minus 1/2 of a. And then we can interchange these and then combine that a with a minus half of a to get a total of 1/2 of a plus 1/2 of b. So that's our answer, that the vector c is 1/2 of a plus 1/2 of b. We could sometimes say it's the average of a and b. That's an important formula, and here's a generalization of that to a somewhat different situation, where instead of dividing the segment AB into two equal pieces, we're going to divide it into two unequal pieces. So suppose that we've divided AB into 5 equally spaced pieces, and we've chosen our vector C so that it's 3 in this direction and 2 in this direction. Okay, so there's 1, 2, 3, 4, 5 equally spaced points, and we're going along 3 in this direction, and there's still 2 more steps on that direction. So this is in the ratio 3 to 2. That's another way of saying where that point C is. And again, what we want to do is we want to describe this point C by describing the vector C from our observation point. And we want to express C in terms of the vectors A and B. And again, as before, the vector joining A to B, which is this vector here, and I've written it over here so you can see it more clearly, it's the same vector. That vector is B minus A, because it's going from the head of A to the head of B. So how do we describe the vector C? It's the sum of the vector A plus this vector. And this vector is 3/5 of the vector AB. In other words, 3/5 of B minus A. And then when we use our laws for vector arithmetic on that, the A and the minus 3/5 of A combine to give 2/5 of A. And we have 3/5 of B. Now both of these are special cases of a more general formula, and we need to understand that general formula. So here's the general situation. There's our point A and our point B on the line L as before. There's our observer point, the vector A, the vector B. There's the vector B minus A. And I want to consider a point C that's somewhere on this line. Doesn't have to be in between here, but it's somewhere on this line, described in the following way. That we're going from here to there via the vector A, and then we're going some multiple of this B minus A. Now in the previous examples we used multiples of 1/2 and 3/5. But now we're going to use a general multiple. So we have to introduce a letter. Let's introduce a Greek letter, because Greek letters are often used for numbers in this situation so that they're not confused with vectors. So let's say lambda. So we're taking the vector A plus lambda times B minus A. What is that when we simplify it? Well, it becomes A minus lambda A plus lambda B. And then the A's are multiplied by just the factor 1 minus lambda. And B is multiplied by lambda. So this combination is called the general affine combination of A and B. And what makes it an affine combination is that the coefficients add up to 1. So let me show you the cases that we've already looked at. The case when lambda is equal to 0, what would that be? If lambda is 0, that's 0, and we just have A. So right here, that's the case lambda equals 0. If lambda equals 1, then this becomes just B, and that term disappears. So we're just talking about the point B. So right here, that's lambda equals 1. If lambda is equal to 1/2, that's our midpoint that we've talked about already. If lambda is 3/5, that would be somewhere over here. And something like this one here, well, it's going to be more than 1 because we're taking a multiple of this vector. So this vector here is maybe roughly 1.5 times this vector, or let's say it's 5/3 of this vector. Okay? So this point would correspond to lambda being 5/3. If lambda is between 0 and 1, then we're talking about something between A and B. If lambda is bigger than 1, then we're on this side. And if lambda is less than 0, over here, then we're talking about on that side of A on the line L. So here is lambda bigger than 1. Here in this range, that's lambda between 0 and 1. So what we have here is a way of describing this line L. We can now think of L as being described by this family of vectors, all emanating from our observation point. I should call it O here. Here's our observation point. In terms of the vector C joining O to an arbitrary point. And as lambda varies, we can get any point on this line. So it's a way of describing the line parametrically. It's a general line with reference to these fixed vectors A and B specified by 2 particular points on the line. It's a very important idea, this idea of making an affine combination. And the critical thing is that these coefficients add up to 1. That's how you recognize an affine combination. It's worth pointing out that there is a very special vector in linear algebra, which is perhaps the simplest vector. It's the 0 vector, the vector that doesn't go anywhere, whose starting point and whose end point are the same. So it's a little bit hard to draw it because it's so small it doesn't really go anywhere. We might write it as the vector from A to A, although that notation is rarely used. But it's really just the vector that starts there and stops there. It has the property that if you add it to any vector v, you still get v. And if you take any vector v and you multiply it by 0, that means you're scaling it right down, then you're going to get this 0 vector. And here's another very important concept that's going to play increasingly crucial role as we develop linear algebra. It's the idea of 2 vectors being linearly independent. So we say 2 non-zero vectors, u and v, are linearly independent precisely when they are not multiples of each other. So if they are not multiples of each other, then they're independent. For example, here's a vector u, here's a vector v. These are linearly independent. If we multiply u by a scalar, by a number, well, we can get bigger vectors in this direction, or smaller vectors in this direction, or maybe vectors pointing in this negative direction. But they're all going to be in the direction of this line. None of them are going to be off in this direction. These vectors are linearly independent. However, these 2 vectors, u and v, they're in parallel, and so one of them is a multiple of the other. Which one is a multiple of which just depends which way we want to write it. So we could say that v, say, is 5/9 of u, or we could invert that and say that u is 9/5 of v. In either case, these 2 vectors are not linearly independent. We usually say that they're linearly dependent. One is a multiple of the other. All right, now we're going to have a look at a few applications of vectors to theorems in geometry. And we'll start off with a theorem that we've already talked about previously. Now we're going to give a proof. It's the theorem that the diagonals of a parallelogram bisect each other. So here's a parallelogram, A, B, C, D, and its opposite sides are equal vectors. This vector is the same as that vector, and this vector is the same as that vector. That's a parallelogram. And the 2 diagonals are intersecting at this point E. So let's just agree that the vector v is AB, and that's also the vector DC. And u is the vector AD, which is also BC. Then AC, from here to here, is u plus v. While BD, from here to here. That's the difference between vectors. It's going from here to here, so it's u minus v. So it's easy to express the diagonals in terms of v and u. And now let's look at AE. That's a vector which is a multiple of AC. And right now we don't know what that multiple is. We think it's 1/2, but don't know yet. So let's just write lambda of AC. So it's lambda times AC was u plus v. We'll write like that. Now, it's also AE, the vector that we get by first going this direction and then going some multiple of BD. Okay? Again, we think it's 1/2 of BD, but we're not sure. So we'll write V plus mu of BD. Mu is another number which we don't know. And BD is u minus v, so we substitute there and we write V plus mu times u minus v. These are two expressions for this vector. So we can equate them. This one is lambda u plus lambda v, and that's equal to this one, which I've written as mu times u plus 1 minus mu times v. So there's a v and there's a minus mu times v. So altogether that's 1 minus mu times v. And now look at this equation. We're going to make an important observation. We have a multiple of u plus another multiple of v equals another multiple of u here plus another multiple of v. Now u and v are in different directions. And if they're in different directions, then there's only one way of writing any other vector as a combination of u and v. Think of going back to our grid plane idea, that every vector in the plane can be written in exactly one way as a multiple of v and a multiple of u added together. So when we have two expressions, this combination equals this combination, then it must be that the two coefficients of vector u on both sides are equal, and the two coefficients of v on both sides are equal. So lambda has to equal mu, and lambda here has to equal 1 minus mu. Well, if lambda equals mu, this equals this, so then when we bring that to the other side, we get 2 lambda equals 1, and so lambda equals 1/2. And so mu equals 1/2 as well. So we've established that lambda equals mu are both equal to 1/2. And that's what we wanted to prove, to show that then AE is really half of AC. And AE is this plus 1/2 of BD. Here's another way of expressing that. We could also have brought all the vectors u on one side, so get lambda minus mu times the vector u, and then bring all the things involving v on the other side, 1 minus mu minus lambda v. And then we can say that, well, the vectors u and v are linearly independent, so it's impossible for one of them to be a multiple of the other, unless that multiple is both 0. So the only way a multiple of u can equal a multiple of v is if the multiples are both 0. Okay, so that means that lambda has to equal, or lambda minus mu is equal to 0. That coefficient has to be 0. And 1 minus mu minus lambda also must equal 0. So that's another way of saying it, which maybe is a little bit more natural. It leads to the same kind of equations that you solve to get lambda equals mu equals 1/2. And so that's proof finished there. The next theorem we'd like to have a look at is this one, which says that the medians of a triangle are concurrent, which means they all meet, meeting at a point G, which divides each in the proportion 2 to 1. So I remind you that a median is a line joining a vertex of the triangle to the midpoint of the opposite side. So there's one median, there's another median, there's a third median, and they're all supposedly intersecting at the point G. And moreover, this is in the ratio 2 to 1, this is in the ratio 2 to 1, and this is also in the ratio 2 to 1. That's what we want to prove. All right, so let's start by forgetting about this median for a second And let's just say that this median and this median intersect at the point G. We will not assume yet that the third median also passes through there. So G for now is the intersection of this median with this median. We'll let the vector AB be U and the vector AC be V. Then the fact that this is a midpoint means that vector from A to D, that's 1/2 of U. And this being a midpoint means that this vector, AE, is 1/2 of V. And now let's describe the vector from A to G in two different ways. Because one way of getting from here to here is to go up here and then down that way. Another way is to go up here and then down there. So the first way, we take the vector U, and then we add a multiple of this vector. So let's ask ourselves, what is this vector from B to E? Well, it's the vector from the head of U to the head of V over 2, or 1/2 of V. And so this vector here from B to E is the vector 1/2 of V minus U. There's 1/2 of V, there's U. The difference is 1/2 of V minus U. And we're taking some unknown multiple lambda of this vector. So that's how we get AG. AG is this plus some multiple of 1/2 V minus U. We don't know what lambda is. Similarly, the other way around, we can write it as V plus some multiple of this vector. Say the multiple is mu. And this vector here is going from the head of V to the head of 1/2 of U. So it's equal to the difference 1/2 of U minus V. So there's our second expression for the vector AG. And then we equate these. So this one here becomes U times 1 minus lambda, because there's a 1 there and a minus lambda there, plus lambda over 2 times V. And over here, how many U's are there? There's a 1/2 of U times mu right there. And V's, there is 1 here and minus mu of them here. So 1 minus mu times V. And again, we have the same situation as we had in the previous proof. U and V are pointing in different directions. They're linearly independent. And we have some multiple or combination of U and V equaling some other combination of U and V. So we can conclude that the coefficients of U on both sides have to be the same. 1 minus lambda equals U mu on 2. And lambda over 2 equals 1 minus mu. Now we have two equations in two unknowns. So I hope you all know how to solve that. You solve that for lambda and mu, and we get lambda equals mu equals 2/3. And that's essentially what we wanted to prove, because that shows that this vector is 2/3 of that big one. And it shows that this vector is 2/3 of that one. And because that's true for any two medians, we just happen to prove it's true for these two, it means it's also true for, say, these two medians. It means that this and this are also in the proportion 2 to 1. So that means that this third median is also going through the point G. Another way of seeing that would be to plug these two values into our formula for A of G. And I'll let you do that to conclude that this vector is then a multiple of this vector from A to F. Okay, so you can see if you can figure that out. Let's have a look at one more theorem. All right, so this is a simpler theorem. We're talking about a triangle ABC, and we have midpoints D and E of these two sides. And the claim is that the vector DE is exactly 1/2 of the vector BC. So in particular, it's parallel to BC and 1/2 of the separation. So we let AB be the vector U, say, and AC be the vector V. Then B to C, that vector, is the difference between V and U. It's V minus U. What about AD? Well, that's half of u, because we're assuming D is a midpoint. That's half of u. And AE is 1/2 of V, because we're assuming E is a midpoint. So what is the vector DE? Well, the vector DE is going from this head to this head. So it's 1/2 of V minus 1/2 of u. Again, the difference between two vectors. And we write that 1/2 of V minus 1/2 of u using the distributive law as 1/2 of V minus u. And V minus u is what we obtained here. That was BC. So DE, that vector, is 1/2 of BC. All right, so that ends our lecture number 2. Here are a few exercises. The first one, exercise 2.1, is also called Varignon's theorem. So I want you to prove that if you have a quadrilateral, so 4 general points, then the midpoints of a quadrilateral form a parallelogram. So I'm taking on each side, I'm taking a midpoint. There's a midpoint, there's a midpoint, there's a midpoint, there's a midpoint. And they connect up to give a parallelogram. So you have to prove that. And here are 2 more exercises, which are also proofs. In linear algebra, most of what we do is a lot of calculation. But every mathematics course should have some proofs in it. Otherwise, you're being cheated of a very important learning experience. So when I ask you to do a proof, I want you to actually write it out. Not just, well, I sort of know how it goes. You have to write it out with complete sentences in a way that anybody could read and follow the argument. So that perhaps even you, in a year from now, will be able to go back and follow the argument and see, oh yes, that's why the theorem is true. So remember, a proof is just an explanation or a reason why something is true. So exercise 2.2, I ask you to prove that the line joining one vertex of a parallelogram, there's a parallelogram, there's a vertex, the line joining that vertex to the midpoint of the opposite of an opposite side, there are 2 opposite sides, so you choose either one, trisects a diagonal. So this diagonal is trisected by that line in the ratio 1:2. And exercise 2.3, prove that the lines joining midpoints of opposite sides of a quadrilateral bisect each other. Got a quadrilateral. Again, we're looking at midpoints of the sides. You join opposite midpoints. That this point I bisects each of these 2 segments, which we can say is the vector EI is equal to the vector IG, and the vector HI is the same as the vector IF. So that's good. That's quite a lot of material. Even though this is less than 1 hour, it's still probably more than most standard lectures at university level for 1 hour, because I'm talking rather concisely and I'm packing in a lot of information. So don't be dismayed if you have to go very slowly and carefully and pause and rerun, go over certain sections a number of times if necessary. You want to understand everything, all right? Don't let any one thing slip by you. Next time we are going to talk about a little bit of application of vectors. We've already established enough material to do some applications to physics, and we're going to talk about centers of mass and barycenter coordinates, which is a sadly neglected topic which should be in every linear algebra course, but unfortunately isn't. So I hope you're going to join me for that. I'm Norman Wahlberger. Thanks for listening.